Okay, quiz 14.3 on the Arrhenius equation. This one is including kind of a lot of different ideas. So the first question, name the two conditions required for a molecular encounter to lead to a reaction. So there are two considerations. One is energy. And so a collision needs to have sufficient kinetic energy to overcome that activation energy barrier. And two is what we call sterics, which is kind of a blanket term for all of the different factors, like that they need to be facing the right direction, they need to be twisted the right way, they need to come together in the right orientation in order for the reaction to proceed. And if they collide in the wrong orientation, the reaction simply can't happen. The atoms aren't in the right positions to break and form bonds in the way that they need to. Question 2 here gives you a picture of a reaction coordinate diagram, and you're supposed to label all the different parts, C, D, and E. So A is over here on the left side. It's the reactants. B is up at the top. It's the highest point in energy along the entire reaction coordinate diagram. We call that the transition state. Okay, C is on the far right side. Those are the products. D is the energy gap between the reactants and the transition state. So this is the activation energy, and E is the energy gap between reactants and products. This is just the enthalpy of reaction, delta H of reaction. Okay, so I guess this is, yeah, that was question 2. So question 3 gives you this table of data and asks to find the activation energy and the frequency factor. So we're going to use two different equations here. The first one for the activation energy says that the natural log of K1 over K2 is going to equal the energy of activation over R times 1 over T2 minus 1 over T1. So for our data here, that means the natural log of 1.6 times 10 to the negative 4th inverse molar inverse seconds over 8.7 times 10 to the negative 4th inverse molar inverse seconds. That is going to equal our unknown energy of activation divided by R, and this R is 8.314 joules per mole Kelvin. And then 1 over T2, that's 42 degrees Celsius. We better add 273 to that to get 315 Kelvin. That conversion from Celsius to Kelvin is essential. And T1 is 15 degrees Celsius, that's 288 Kelvin. Okay, now this is a bit intimidating to look at, but it's actually really straightforward to solve. You've got a natural log function on your calculator, so you can just take the natural log of this divided by that, multiply by 8.314, and then you can use parentheses to sort this all out. And I actually solved it without calculating any of these intermediate values. I just said EA is equal to the natural log 1.6 over 8.7 times 8.314 divided by quantity 1 over 315 minus 1 over 288. And anyway, I get an energy of activation equal to 47,300 joules per mole. And we'll often report that as 47.3 kilojoules per mole. Now that's the energy of activation. How do we find the frequency factor? Well, the frequency factor drops out of that 2-point form of the Arrhenius equation. So let's just go back to the original Arrhenius equation. That is that the rate constant is equal to A times e to the negative EA over RT power. And we'll just pick one of our two trials. Let's pick trial 1. K is 1.6 times 10 to the negative 4th, inverse molar, inverse seconds. That's going to equal our unknown frequency factor times e raised to the power of negative 47,300 joules per mole over 8.314 joules per mole Kelvin times, 288 Kelvin. And again, we can just solve this really directly with a calculator. And A ends up equaling 60,700 inverse molars, inverse seconds, which is a lot smaller than the other frequency factors we've seen so far. And so we can infer from this that either the molecules involved are very large and slow moving, or the reaction has very strict orientational constraints. The steric factors are very restrictive, or a combination of both. And so there's only 60,700 collisions per second per molar in this reaction. Okay, and the last question, what is the overall reaction order? Now, I didn't give you any information to determine the reaction order except for the units of K. The rate constant is inverse molar, inverse seconds. What do those units imply? Second order overall. You can get your units from the overall reaction order, and you can get your overall reaction order from your units. That's quiz 14.3.